my letters white, so it is a slightly different version today, and hopefully this is going to be more visible also for the people that are in the room. Now, before starting the main topic of today, which is, as you remember from the program, the microscopy techniques using synchronous radiation, the different kinds of interactions, and so on and so on and so on. I would like to spend a few minutes following a question yesterday, which I found very interesting. As you remember, there was the question when we are talking about the outstanding role that synchronous radiation played during the COVID pandemics. And so the studies to identify crucial structural information for the virus and its components. The question was, but how much did it cost? I mean, how much did the people have to pay in order to make this analysis? And we mentioned yesterday that actually the answer is zero, because a decision was immediately made to share the information. And I think that this stimulated me to elaborate a little bit on this, because this is really the most important historical application of synchronous radiation. So I have a couple of transparencies just to complete that topic. So, first of all, what happened when this race to solve the structure mystery of the COVID started? It was almost a mystery movie. So first of all, on January 26 of 2020, which was the first period of the pandemics, there was a phone call from the colleagues, the Chinese colleagues in the Shanghai synchrotron to the Diamond synchrotron in the United Kingdom. And they had a very important piece of news, that is, they had just obtained the very first structural data on the COVID virus. And so that was very interesting, but there was a huge problem. That is, the Shanghai synchrotron was scheduled for maintenance. So you had to shut down in order to, you had to shut down for maintenance. And it was impossible to stop that. And so all suddenly the Chinese colleagues could not continue this line of analysis. But they were really illuminated, because what they did was to contact Diamond, give them all the information, and tell them, you take the flag and you go ahead. All right. So it was a fantastic show of the solidarity. And of course, Diamond took the challenge. In a few weeks, they've been able to solve the practical problems. For example, to get the first crystals of proteins that were large enough in order to perform crystallography, that is X-ray diffraction, as we shall see later. And we started generating the data. And almost immediately there were other synchrotrons that started joining, and in the end the majority of the entire network was heavily involved, in spite of all the practical difficulties of traveling and accessing the facilities during the pandemics. And as I mentioned, because of this openness that is making the data available to everyone, the path to the virus vaccines and the drugs became very rapid, and this had an important impact both socially but also financially. And I'd like to spend another transparency in order to understand a little better this last part, because I mentioned just the total figure, but I think it's interesting to have a closer look. Now, first of all, there is this provocative question. How much in cash is worth the structure of a virus? Well, it's difficult to answer because in order to understand really what is the impact, you must find out what was the cost of the pandemics. And there, even giving a definition is not completely easy. For example, you can argue that if somebody loses his father because the father dies in the pandemics, then of course it is a devastating human experience, but it has also an impact on the economy because the productivity of the guy is going to go down and so on. All this is extremely difficult to quantify, and so you understand that a good analysis is quite difficult. But I'd like to propose to you this short study by Cutler and Summers, which is for the United States and for a 2-year period from the start of the big pandemics. And what you can see here is that basically they believe that the cost was $60 million for the, excuse me, $60 trillion, millions of millions, trillion of dollars for the United States. Now, I try myself to prorate to the entire world by just using the ratio between the, excuse me, because this is keeps going on. All right. So I prorated by using the ratio between the gross national product of the world and that of the United States. And the estimate is that basically the cost was $64.5 trillion for the 2-year period, which means about $32 trillion per year. Now we can convert this into an estimate how much was the money that was saved by stopping the pandemics, using the viruses and using the results of the structural investigations using synchrotron radiation. Now, there is still some difficulty because you had to analyze by how much the virus has shortened the critical period of the pandemics. However, I believe that if you're using as models the previous pandemics of the century, previous century, for example, the Asian flu or the Spanish flu, then you can understand that these were going on for many years, making damage during many years. And so I think that it is quite safe to conclude that at the very least, this operation that led to the virus shortened by at least 1 year. I think this is a very conservative, probably was more than that, but let's assume 1 year. That means $32 trillion. So this is how much, see? Yep. Okay. Okay. Yeah. The bottom line is that, let me say that in English, because I found there was indeed a problem in the translation. And so it is $32 trillion. Okay. So that's my comment. But basically, what you can say is that the savings were at least 1,000 times more than all the investments. And so constructing synchrotrons has been a very, very wise kind of investment. Now you can use different kinds of reference for that. Leo yesterday made a comment about the military expenditures. There is a possible political problem there because conservative people may consider military expenditures as something necessary. But you can use other parameters. For example, how much we are spending in McDonald's every year, or what is the total investment in gigantic cruise ship that are creating all sorts of problems around. And you can still see that what we are spending for science and technology in general, but in particular for the network of synchronous radiation, is not only very reasonable, but in fact very limited. Okay, so this is what I wanted to say. Now, let me stop for just a moment and see if there are any questions or comments about this provocative and highly political statement. Questions? No? All right. So I convinced everyone, I hope. All right. Let me go on now and start from where we stopped yesterday. It is, we spent a lot of time discovering how, starting from relativity, we can discover a number of important properties for synchronous radiation. Actually, this list is almost complete. The only thing that is missing is coherence. Now, keep this word in mind, because I decided to delay a little bit talking about coherence, since coherence is directly related to the main microscopy subfield of synchronous radiation. But anyway, this is where we are right now. We discovered all these properties of synchronous radiation. And I hope I convinced you that you do not need to have tremendous equations or very complicated theories in order to extract the basic facts and understand what's going on, and perhaps make a better use of the facilities. All right. Now, let me now go to the question where we stopped yesterday, that is, if these efforts in order to develop the synchronous radiation network were justified in spite of involving quite big resources. And we made several arguments here. Let me just go through them rapidly. First of all, a single storage ring is supporting very many experiments in parallel, can go up to 100 or even more. Second, the lifetime of a facility is not short, it's 25 to 35 years, or as I mentioned yesterday, even more. And so all this is spreading the cost. And now there is the other important aspect, that is that there are very many ways in which X-rays can interact with matter in a form of molecules or solids. And each one of these physical mechanisms or chemical mechanisms can be exploited for different kinds of applications. We shall elaborate on this in a moment, but let me just mention that there is this bottom argument of why this is so, and this is that the wavelengths of X-rays and the photon energies of X-rays are commensurate with parameters of chemical bonds. And so the X-rays, in particular, the X-rays coming from synchronous sources, especially those, are the best probe of chemical bonds. And if you analyze today what we are studying in science and technology, with a very, very few exceptions, we are talking about problems that are directly or indirectly related to chemical bonds. And so that's an important conclusion, because a synchrotron, a storage ring, is not a specialized instrument. It's not something that has been built only for one technique or for a subset of technique. It can be applied to very many different techniques. It depends on the instrumentation that is available around the ring in the beam lines, but basically it is a very versatile machine, and therefore this increases the return. And the other aspect is that although the entire field was started by physics, but then chemists arrived, and then the biologists, the material scientists, and now we also have people involved in environmental research, arts and humanities, microfabrication techniques. And so this is not only a versatile instrument for a variety of techniques, but it is also a multidisciplinary instrument which is used by many different communities working in parallel and quite often interacting between them. So it is also a seeding ground, a fertile ground for interdisciplinary collaborations. All right. Now, I don't have the time today or tomorrow to present a complete picture of all the techniques, but let me start from some examples, okay? First of all, imaging. Imaging, that is radiography, or is the oldest technique using X-rays, and still is the most widely used for a variety of techniques. That's one example of a result that came a few years ago. We became interested in the mechanism that allows fireflies, the lucernagas, to emit radiation. This is a chemical mechanism, and if you're looking at the parameters, it's just unbelievable. Okay, that is, if you try to scale up the entire emission, and suppose you want to do something like that by emitting light from a plane, emitting energy, well, the plane will crash in a few minutes. There's so much energy that is emitted that actually the fireflight becomes a very, very effective kind of light-emitting instruments. So the mechanism is still not understood. And let me show you one reason. This is a microscopic image of the organ that is responsible for the chemical process. The important point is that by using synchrotron radiation and the special characteristics of radiology with very high resolution, we have been able to see all this very complicated system of tubes where the chemical reactions are taking place. Now, before synchrotron radiation came into the scene, it was not possible to see all these tubes. And therefore, you could have an idea of the general structure, but you could not test quantitatively the different models for the chemical production of light, because to do that, you needed the complete network of tubes. Now, if you zoom, now you see that with synchrotron radiation, we can indeed get a complete picture, including the smallest tubes. And this is allowing us to start making reliable quantitative assessments and making some steps ahead in trying to understand this fantastic mechanism. And perhaps, who knows, start to use this a similar kind of mechanism for practical applications. So that's one example. Let me go to another one. Excuse me, before going to other ones, I need to tackle the property that we set aside until now, okay, that is coherence. So besides being intense, collimated, polarized, and so on and so forth, the synchrotron X-rays are coherent. Now, this word is well known in physics, perhaps not so much in other domains. So let me try to propose to you a very simple approach to understand what is coherence. In simple terms, we can say that coherence is the property that allows radiation to cause wave-like effects, like diffraction or interference. In normal life, there are a lot of light sources around us, starting from the sun and lamps and so on. But seeing these kind of effects, the interference or diffraction, is not very common. There are cases in which see them, but in general we do not. And the reason is because most of the sources of light around us are not really fully coherent. And so, in order to get this kind of wave-light effects, we need sources that are coherent. In order to understand what is coherence, we can use any kind of phenomenon. Let me start, for example, from the double slit diffraction. You can see here a screen with two slits. You can see a fluorescent screen, but if you're sending incoherent light, you get nothing. I mean, you illuminate the screen, the fluorescent screen, but you don't get an interference or diffraction. Now, let me propose instead a coherent source, a laser. I'm sorry because in my changing colors, I think that I blurred. So it says radiation from a coherent laser. And now with a coherent kind of source, we do get a diffraction pattern. So what makes the difference between the incoherent source and the laser, which is a coherent source? Well, we must realize that there are actually two kinds of coherence. And in order to understand this point, let me start from an idealized case. Okay, the idealized case is that of a source of radiation, which is a point source, no geometric dimension. And this point source is also fully monochromatic, meaning it only emits one wavelength. If these are the conditions of the source is fully coherent, and we are always going to get interference or diffraction. In this particular case, we are seeing the diffraction from a pinhole. However, we must be more realistic. And so let me start relaxing these conditions and suppose that instead of having a point source, we have an extended source, and or instead of having a fully monochromatic source, we have a source that emits a band of wavelength. So you start seeing that actually there are two kinds of coherence, one that is related to the geometry of the source, and the other is related to the spectral characteristics, that is the emitted bandwidth. And so we had to analyze the two kinds of conditions, starting, for example, from what is called the time coherence, which is the coherence that is related to the bandwidth. Now, how can you understand this kind of coherence? Well, the simplest way is to realize that basically each one of the wavelengths in the band of wavelengths is producing a diffraction pattern. And what you see on the screen is the superposition of all the diffraction patterns. When you start doing the superposition, you may end up having just a blob. Okay, you don't see fringes anymore because the superposition has broadened them, and so you just get a blob. You don't get a pattern anymore. If this is not happening, if you still see the diffraction fringes, then there is time coherence, and this is the first kind of coherence. Now I'm ready to go to the second one, which is the spatial coherence. In this case, what you can imagine is that each point of the extended source is producing a different diffraction pattern. Once you see what happens in the fluorescent screen, you realize that you're going to have a superposition, and the superposition may or may not allow you to still see fringes. And if the source is too much extended, you don't see fringes anymore. But if you still see fringes, in spite of the fact that the source is no longer a point, then you have what is called space coherence. So this gives you the two kinds of coherence, and both of them are very important for the X-rays emitted by a synchrotron source. So let me amplify this discussion a little more and start from the time or longitudinal coherence. Here we see two different wavelengths, their patterns, and then you put them together and you may get too much blurring. So what are the conditions for still seeing the fringes? All right, the analysis is very simple because elementary optics is telling us what is the distance between adjacent fringes. And you can see that it is a very simple formula. Now, if instead of having one wavelength, we have a band of wavelength, this condition that is the X parameter is going to be broadened. And you can see here that very simply it is given by the same formula as before, but only that instead of having lambda, you have delta lambda. Now, when is that you still see the fringes? Of course, when the broadening is not bigger than the distance between adjacent fringes. And so you are getting this super simple condition that is time coherence requires the relative bandwidth to be smaller than 1. This is the condition for time coherence. Let me make a short parenthesis here because this could be interesting beyond synchrotron radiation. I mentioned before that seeing diffraction of interference effects is a rare event in everyday life, but sometimes it happens. Okay, if you have a rain, after the rain there are thin films of water around you. Quite often you see these beautiful colors coming from essentially wave-like effects. How does it come that we are getting now an effect that requires, for example, time coherence? That is, how do we get this delta lambda over lambda smaller than 1? Now, this is related to the fact that our eyes only detect a portion of what is emitted spectrally by the sun, the portion that is the visible radiation. And if you're looking at the bandwidth of visible radiation with respect to the center, which is the green, you realize that you get this condition, and that's why you see this kind of phenomena, although they are quite rare because you need all the necessary conditions. Now, there is another way to express the same condition by introducing an important parameter that is very often used in synchrotron radiation, which is the coherent or coherence length, which is essentially lambda square over delta lambda. And you can see immediately that there is time coherence if the coherence length is longer than the wavelength. Okay, so this is the condition for having the time coherence. Keep this in mind, in particular the fact that in this parameter there is a lambda square, because this is playing a role that we'll discover more a little bit later. Okay, so much for time coherence. Now we go into space coherence. What you see here are 3 points that are emitting, and we are getting superposition of patterns in the pinhole diffraction phenomenon. And once again, the superposition may just blur the fringes too much. Once again, the analysis for finding the conditions for still seeing the pattern are, again, very simple. I will not go into the details because there are really very simple kind of calculations. You can take, once again, the distance between two adjacent fringes, and you must require that the maximum distance of emitting points in the source must not be such that the blurring is bigger than the distance between fringes. You can work out the condition, it's quite easy. And what you get is this condition for lateral coherence, this one. Okay. Now, as you see, once again, is a reasonable condition that requires a source of a limited size, so that the term on the right is big enough that you can get this condition easily. Okay. Delta, I apologize because once again, by putting white, this one here is delta. Okay. So delta is the size of the pinhole, and this is what you see here. I'm sorry, I cannot rechange the color now, but please believe me, it is delta. Now, all this is very interesting, but actually there is a more interesting way to express the same condition, which is also easier to understand in the case of synchrotron sources. And this is by realizing that once you see how much of the emission of a source is participating in the diffraction phenomenon, well, you realize quite easily that it is only a fraction, it's not all the emission. Why so? Because in order to produce a diffraction pattern like this, the emission must go through the pinhole. If it does not go through the pinhole, it's not participating to diffraction. And so what is participating to diffraction is what is emitted in a rather narrow solid angle, which is given by these distances. So that is the size of the source, once again, delta, and the distance between the source and the pinhole. So the portion of the emission that actually participate in the diffraction is that in the solid angle delta square over d square. We can put these two conditions together, okay, and we find that this is actually smaller using the condition for coherence, lateral coherence, than lambda square over c square, xi square. And so we can manipulate with just one step, and we are getting to this conclusion, that is the parameter that really defines the coherent power or the coherence, the lateral coherence of the source is lambda square divided by the size of the source, c square, and divided by the solid angle gamma. And so this is called the coherent power factor. If it is big, then there is spatial coherence. So now we have the two conditions refined for time and space coherence, the coherence length on one side and the coherent power on the other side. And now we are ready to leave general optics and go into X-ray optics. The million-dollar question, of course, is the sources of synchrotron radiation are giving coherence. Let me start from the spatial coherence. The answer is yes, yes, yes. Why so? Well, we have seen that the coherent power is the wavelength squared in the numerator and the geometric parameters in the denominator. But folks, we spent quite some time yesterday to explain that actually the beauty of synchrotron radiation is that the geometric parameters are small, are very small. This is how we applied the analogy of a torchlight. So these parameters for synchrotron radiation are very small. The coherent power is very high. We have a lot of spatial coherence. Now, this realization allows us to expand things a little bit and discover a number of other important properties. Now, first of all, we see that there is a lambda square in the coherent power. And this means that if the wavelength is short, then this limits the coherent power. So in the case of X-rays, we have a fight between the geometric parameters and the short wavelengths of the X-rays. That, by the way, is the reason for an historical fact. Is if you're looking at wildlife phenomena in optics, well, you see that they've been present for several centuries, notably because of the experiments in the United Kingdom and in France. So much before the coherence for X-rays, there was coherence for visible light. And the reason is because the wavelengths are much longer for visible lights. You're talking about perhaps 5,000 angstrom, where for X-rays, you're talking about angstroms. And so even after X-rays were discovered by Röntgen, it took some time in order to understand that there was coherence, because people working with X-rays were mentally programmed not to consider coherence at all, because the wisdom was that with these short wavelengths, you're never going to get it. Well, folks, that's not true. That is, you are getting high coherence with X-rays now. Now, we must not forget that in the coherence length, there is also a lambda square. So the same problem that you have for X-rays for space coherence, you also get for time coherence. And once again, if you're looking at the parameter, you do get time coherence, but in this case, again, it was more difficult for X-rays than for visible light. For example, yesterday we discovered that for ondulators, there is an emission that has a limited and narrow bandwidth. And if you're looking at the definition of coherence length, you realize that this helps time coherence. So bottom line is that we are getting both time and especially space coherence. Now, there is a funny realization at this point. You realize that the geometric parameters we find in the coherent power are the same that we find in the brightness, in the brilliance, the brillo. So what happens is that we don't have to have a separate fight in order to get space coherence. We have been fighting for many decades in order to improve the geometry of synchronous radiation sources by decreasing the geometric parameters, and we got a bonus. We got a bonus because besides getting higher brightness, we also got high spatial coherence. I must make a confession, okay, at this point, which is a confession about something which is historically a little bit embarrassing, because actually the phenomena that are related to coherence were present in the results of radiology with synchronous radiation for a long period of time. But since in X-ray business you don't think about spatial coherence, then many people did not realize what they were seeing. It was only after a while that they realized that the fantastic images, like those of the far flight I showed you before, are a consequence of spatial coherence, which is a byproduct of the effort to get higher brightness. So life is good in some cases. Now, what is that we buy with this spatial coherence? Well, we are getting a fantastic new kind of radiology. We are opening up completely new domains that are totally unthinkable for the medical radiology used even today for medical diagnostics. Because you know that if you break a bone and you go to the hospital in order to get X-rays, the image you're getting is a certain resolution, but is nowhere close to the resolution and the details that you are getting with synchronous radiation. These are, for example, vessels that are smaller than the coronary arteries. And this is one example of how you can take radiographs today, not of a bone, not of a leg, but of a single cell, okay? In this case, we're talking about a neuron and its connections. Now, that's a very important realization, and tomorrow we are going to expand a little bit, talking about what we are trying to do today in order to exploit these characteristics. Okay, so this image formation using coherence then is something very important, and I'd like to elaborate a little bit in order to understand what's going on, okay, and how spatial coherence is getting into the scene. I like to use an analogy, okay. I like wine, and so I'm using red wine. Actually, I like red wine more than white wine. But the analogy is, what does it mean that we are seeing a glass of wine? Okay, actually there are different phenomena that are going on. First of all, there are phenomena of absorption and diffusion, scattering, that is spectrally selective, and this is what causes the red color of the red wine. But this is not the only thing that we see, because in parallel, we are also seeing edges. Now, the edges are glass edges, so they are not absorbing. They are not colored, right? But what happens is that the presence of the edges influences the light, for example, by refraction or scattering, and this is what makes the edges visible. So you have a collection of two different kinds of mechanisms. Now, in the case of X-rays, you can use absorption to have radiographs, and this is what we are doing in normal medical radiology. But if you're looking at the images I showed you before, realize that the quality is to a good extent related to very sharp lines separating different regions. And you can see that they are very sharp, and they are caused by phenomena that are quite similar to those present for the edges of the glass in the case of the glass of wine. So you need to see these sharp edges in order to get the high quality images. And in order to see them, of course, if we have a source of X-rays that is spreading the radiation in all directions, so it is not spatially coherent, because don't forget, in the spatial coherence, there is a solid angle of emission, then in that case, you do not see these effects. But if you have spatial coherence, collimation, and therefore a well-defined direction for X-rays, you do see this phenomena. And that's the link between the image quality for coherent X-rays and spatial coherence. Let me go on a little bit by showing more examples. So these are some early cases of images, and we can start seeing things in a geometry that does not exploit the coherence of the synchronous radiation source. So you see the reasonable images, but quite frankly, they're not very good. Now, if you are readjusting the geometry and you exploit the coherence, the spatial coherence, puff, you see all the details, so you go into microscopy and so on and so forth. And so this is one very good way to get into the microscopy. So much so that before presenting some more results, I would like to be with me for a few minutes in order to understand a little better how you can get how you can exploit phase contrast. Once again, you can make very complicated theories of computer modeling and so on and so forth. But a few years ago, Giuliano Tromba in Trieste and myself decided to start looking at things with a simplistic point of view. And so we developed a model also together with Yuhan Wu, which is the following. Suppose that you have an idealized object in which there are two regions with different X-ray refractive index, and then you're going to get a slanted edge that separates the two regions. Now we have a detector, and we are trying to get images by sending radiation, X-rays. Now, first of all, you can see that for regions that are not interacting with the edge, you get nothing. That is, the X-rays are simply going ahead. But if you are now getting X-rays going through the edge, then there is refraction, and refraction is changing things in a very simple way. You get a sequence of light, dark lines. Light, dark. This one is dark, this one is illuminated. So if you're now making a prediction of what I'm going to see in my image, well, you predict that you're going to get something like this. And if you're looking at some of the images I showed you before and zoom in, you realize that exactly what's going on. So this is what's going on. Essentially, you can get these sharp lines because of this edge phenomena. And once again, it is quite important to realize that this is working if the X-rays have a well-defined direction, that is, they are spatially coherent. It does not work if they are going in all directions. Now, one important parenthesis here is that this condition for space coherence is not going together with a condition for time coherence. Actually, time coherence is not important for this kind of imaging, which is very good because many people are thinking about using synchronous radiation in terms of monochromators that are decreasing the bandwidth and give you also time coherence, but you don't need them. Actually, for image taking of this kind, you can get rid of monochromators, get a lot of more radiation, and improve the efficiency of the entire process. All right, so now it's time to start looking at how we can use this kind of process. I'd like to show you a couple of examples, and then we are going to get into questions. Please get ready for questions. And then we are going to take our coffee break of halfway in the presentation. All right. Yesterday, Leo presented some results about the manuscripts in Pompeii. It's a very interesting problem, but actually the problem of reading ancient manuscripts is much bigger than just this specific case, which is very important. Actually, the vast majority of the manuscripts that are still preserved from the old centuries, they are not used at all. They are not used at all because there is too much information, and if you don't get a digital version of the information, then you cannot process it and you cannot get into something reasonable. What is something reasonable? Well, that one problem in opening and reading ancient manuscripts is the fact that they are fragile, they are vulnerable, they are at risk. If you open them, you can destroy them. And furthermore, turning pages and taking images of each page is a long process. So if you are taking a big collection, like for example the Venice Historical Archive, which I've been studying for several years, then you realize that you need some kind of different process. A different process can be of taking X-ray images page by page, and without opening the manuscript, you can actually read the content and get a digital version of the content. Now, I mentioned the Venice Archive, and this is a project that is going on. It's quite important because this is not an archive for literature or art. It's an archive for practical information. For example, there is all the information about the ships that were coming from the Far East or from the Middle East to Venice. And a lot of the history of Europe can be decoded using this information. For example, you can discover that spices were rare, and therefore people were starving in Europe, and this started wars. and it is a much more plausible cause than all these fairy tales about a king that wants to marry the princess and stuff like that. Now, besides the cases in which you need to handle a big volume of information, there are also other practical cases. There are examples in which you cannot legally open a manuscript because, for example, the family of a testament disappeared and you don't have the permission to open. Well, we started looking at these documents, and that's one example of a document by a noble lady in Venice that many centuries after having written the testament had sealed that, but no one could read it. And now you could start reading it. You can see here the beginning in which the lady mentions God to ask help in redacting the testament. So that's one example in which we can exploit the properties of coherence in correlation for imaging. Maybe going on and try to broaden the perspective, but actually I think this is a good time to take a stop here, have a coffee break of 5 minutes. But before, let me see if there are any questions. Is somebody still there? No questions. All right. So let me propose then a 5 minutes coffee break, and then we'll restart from this point. Okay? it's okay for everyone. I would like to restart. Okay? Can you hear me? Can I restart? Great. So this is where we stopped during the coffee break, and the idea here is to go beyond the individual examples and try to get a broader, more general point of view, expanding the argument that we already made. That is, that there are many different interactions between X-ray photons and solids or molecules, and each one of these is producing one or more experimental techniques. Here, you don't have a complete picture. You have a subset of interactions and a subset of techniques. The broader picture is much, much wider, but the basic message is still there. That is, you're getting a variety of techniques. One important point is that many of these techniques can be implemented in a microscopy mode. As a matter of fact, if you're looking at the red frames, realize that almost all the techniques and almost all the interactions can be implemented basically in a microscopy mode with high lateral resolution. And so this gives a number of techniques, and once again, I don't have the time to look at all of them, but I would like to spend some time for each one of the main categories. First of all, let's talk about the techniques that are related to absorption, which is the complementary mechanism in radiology with respect to the phase contrast phenomena that are related to coherence. So that's the nickname for the kind of phenomena we just analyzed. But then there is still absorption. Absorption is an important component. And so we need to understand a little better how X-rays are absorbed by materials. Let me start with the simple case of an insulating solid. The objects in the solid that are responsible for absorbing X-rays are the electrons. And so we need to understand what is the energy distribution of electrons. During the formation of chemical bonds, we are creating a valence band, and we also have a conduction band. These are essentially the anti-bonding, the bonding and the anti-bonding chemical states. There are also electrons that are not directly involved in the formation of chemical bonds, and these are the core electrons. Those are down in energy, and so they do not participate directly in chemical bonds. Now, what happens when we send X-rays into the system? Well, this is a photon, and you can have, for example, the excitation of one electron from a core level to the conduction band. Now, you need to have this mechanism because in order to allow the transition, you must start with an occupied electronic state, but you must end up in an empty state. And in an insulating solid, the conduction band, at least at zero temperature, is empty. And so you have phenomena of this kind, and you have large distances in energy that allow you to absorb X-rays. So what are the consequences on the spectroscopy? Well, if you're looking, for example, at the absorption as a function of the photon energy here, you realize that there is no absorption until the energy of the photon is not sufficient to bring this electron to at least the bottom of the conduction band. If the energy is like this, the electron cannot make a transition, cannot absorb X-rays because there is no final state. And so we are starting to have absorption when the energies are above this bottom of the conduction band. And so there will be an edge here in the absorption as a function of photon energy. It's a characteristic which is extremely important because these edges, as we can see, are revealing the presence of the core levels, where is the initial state for the transition, and each core level is related to a specific atomic species and therefore to a specific element. So by just seeing that there is an edge, you can immediately say in the sample there is such and such element. And that's the most basic information you can get with absorption. And of course, you can perform the same kind of analysis in a microscopic way, for example, by focusing X-rays and getting the absorption for a small area of the sample. And so that's once again, it is the most basic kind of information. But it is not the only kind of information you're getting from absorption edges. In fact, if you're looking at the real absorption edge with a real spectrum, well, you do see the edge. But then afterward, there is a series of structures, and actually there are structures that are close to the edge, but also what is called the EXAS, or extended X-ray absorption fine structure. And this information is much bigger than the one you're getting from just the presence of the edge. And so we must realize how this information is related to the important properties of the solid and how we can use it. So in order to do that, let me have a closer look at the mechanism that is causing all this fine structure beyond the absorption edge. Now, suppose that you are looking at a solid, and for simplicity, we are only showing two atoms in the solid, the one that absorbs the X-ray photon, and another atom in the neighborhood at a certain distance d. Now, we are sending the photon, the X-ray photon, and we are exciting an electron in the conduction band. The electron in the conduction band is free to expand, and in quantum mechanics is going to expand as a wave. So you're going to get an outgoing wave starting from this absorbing atom, and there it is. However, this wave hits the neighboring atom, and it is partly reflected. So if you want to have a complete picture of the phenomenon, you must take into account that there is an interaction between the outgoing wave and the backscattered wave. To make things very simple, since these are waves, then the interaction can be either constructive or destructive, and this depends basically on the wavelength of the electron, which is related, as we know, to the photon energy, therefore, to the electron energy, therefore to the energy, which in turn is related to the photon energy, because if you are putting more energy with a photon, you're getting more energy for the electron. And it is also related to the geometry, to this distance. So this gives rise to this sort of oscillations that we call the EXAS, okay? From the oscillation, from this constructive or destructive interference, we can get information about, for example, this distance. And that's extremely important because we can now get structural information, not about the entire crystal or the entire solid, but only about what's going on in the neighborhood of the atom that absorbed the photon. And so we are getting geometric information that is very, very much localized. This information is quite important. That's why XRs have been one of the main techniques for synchronous radiation for very, very many years, including the microscopic version. Now, let me leave absorption and go to a question. That is, what happens to the energy that has been absorbed by a solid by absorbing X-rays? Well, there are several different ways in which this energy can be utilized, but in particular, it can produce the emission of other photons. How so? Let's look again at the energy structure of the electronic states. And we can see here an incoming photon, and the incoming photon is kicking out one electron from a core level. This is the mechanism that we just analyzed before. But now there is an unstable situation because there is an empty state here. There are occupied states at higher energies. Of course, the system is unstable, and therefore there must be some kind of mechanism to make it stable again. And one possible mechanism is indeed an electron from a higher level jumping down to the core level and losing energy in form of a photon. So by analyzing this X-ray photons, we are still talking about X-rays because the distances are big, we can once again analyze or identify the presence of certain core levels, certain atoms, and therefore certain elements. And so this is another kind of techniques for chemical analysis, which is very popular. Actually, you don't even need synchronous radiation in order to implement this technique. It's called the fluorescence microprobe, and it is typically implemented in a microscopic way by just limiting the size of the X-ray beam, the primary X-ray beam, and it gives you a quick view of the chemical composition. Normally, you don't go much beyond that, but it is very valuable information. Let me just give you one example. We wanted to know in the manuscript analysis what was the chemical composition of the inks that were in the letters. And with this technique, actually, we could get fluorescence spectra from different regions, and we could see all the different elements that characterize the ink. Okay, so this is a second class of X-ray microscopy techniques. And now let me go to a third and very important class. And I think that we are going to occupy most of the time until the end of the lecture today, talking about this class. And we are going to start the presentation of microscopy techniques tomorrow before going into the Synapse project. Photoemission. So what is photoemission? Photoemission is a class of experimental techniques that are based on the photoelectric effect. What is the photoelectric effect? Well, suppose that you have a solid, and in the solid there are electrons, and now you send a photon. Photon can give energy to an electron. The electron can overcome the barrier that prevents it from leaving the solid and going into vacuum. So it can go into vacuum and become what is called a photoelectron. This phenomenon has been very important also for the history of physics because it is one of the phenomena that have been have been analyzed by Albert Einstein in 1905 after formulating the hypothesis of photons. And quite paradoxically, almost all the people are taking that in the wrong way, because the history is that Einstein derived the idea of photons from the photoelectric effect, which is totally wrong from the historic point of view. But I don't have the time to go into that, so let me just set that aside. How can we use the photoelectric effect for experimental techniques? Well, what is important is to realize that this is a way to analyze the state of electrons inside the solid. Suppose that you have one isolated atom, and then the isolated atom start forming chemical bonds with other atoms and forming a solid. What happens to the energies? Well, if you take the energy spectrum of the atom, of course, it is going to be changed by the formation of chemical bonds. The core levels are changing in position. There is the valence band. So you're going to get a new structure. And it will be very, very interesting to explore this electronic structure. But there is a practical problem. That is, as long as the electron is in the solid, it is quite difficult to measure its properties and therefore, for example, to find what are the energies. Now, with the photoelectric effect, what we are doing is to take the electrons, to bring them in vacuum, where we can capture them and analyze and measure their properties. And this is the entire background of the photoemission experiments. In fact, if you're looking at the vacuum, you realize that the energy distribution of electrons in the solid is going to be shifted upwards by the energy of the photon. And so if you are now measuring these energies in vacuum, you can subtract the energy of the photon and you are getting the energies of electrons in the solid. So this was the simplest idea you can imagine, and it gave you a very large number of experimental techniques with one common denominator. That is, in order to implement these techniques, you need a lot of photons. You need a lot of intensity. And that is why all this field really started taking off only after synchronous radiation came into the scene. And after that, it was possible actually to study all the electronic properties in the solid. Let me just give you a few examples of that. Okay. First of all, the fact that this kind of techniques are basically taking book-like notions, like core levels, valence bands, and so on, things that are coming from quantum mechanics, but in the old days were just things you find in books and you could not really touch with your hands. And now you can, okay? Suppose that you take, once again, core levels, valence band, and yet the electrons in the core levels and in the valence band of a given solid. And now you take the photoelectric effect and you are extracting electrons from these states. So you can see where the electrons are. Here, this is the energy already corrected for the energy of the photon, as we just explained. And these are the electrons that are captured. Now, normally you show this rotated, you get this. This is a photoemission spectrum. The photoemission spectrum has narrow peaks that are coming from the core levels and the broad bands coming from the valence band. Now, when I first saw these kind of things, I was a kid. I was a very young investigator. I can tell you that it was shocking for me, because for the first time, instead of reading in the books about core levels, well, I had core levels in my spectra. And so all this changed the perspective about believing or not believing quantum mechanics, because it could transform these notions, these theoretical notions, into things that are very concrete and very tangible. So once again, it was for me a rather emotional experience. Now let me go on. Suppose that we want to see with this kind of approach what is the difference between a semiconductor and a metal. Well, we know that for a metal, we must have electrons close to the top of the energy distribution, which is the Fermi level. And so we must have a spectrum in which the valence electrons are going all the way to the Fermi level. This is an experimental broadening. And we can see here that indeed the metal is a metal, that is, it has electrons that are close to the Fermi edge. This is the Fermi edge. Now, if we are going to an insulator or a semiconductor, there must be no electrons close to the Fermi level. And that is indeed the case for the semiconductor gallium arsenide. Here we see the valence electrons, but no electrons close to the Fermi level. So once again, theoretical notions that are becoming very concrete. And there they are. Now, let me go to another example. Superconductors. Now, in the case of superconductors, the advent of superconductivity, the triggering of superconductivity, is also related to the energy of the electrons, but it is a phenomenon that only occurs at low temperature. And why so? Because there is, again, a gap, okay, that is preventing the mechanism for resistivity to kick in, a gap in the energy spectrum of the electrons, which is much narrower than the gap that you find in a semiconductor. So, theoretically speaking, we know that if you're making a comparison between a normal state and a superconducting state, then once you lower the temperature and you go from the normal to the superconducting, then there is here a gap. Okay, and this gap has been a theoretical hypothesis for decades, starting from the famous work of Bardeen, Cooper, and Schrieffer, the BCS superconductors. So everyone believed that it existed, you could see it with infrared spectroscopy, but you could not really touch it directly. Why so? Well, because if you try to use for the emission spectroscopy to study this phenomenon, then you are hitting a huge barrier. The barrier is that the superconducting gap is not the electron volt wide gap of a semiconductor, is much, much narrower, and you need good energy resolution in measuring the energy of photoelectrons in order to see this gap. And this just did not happen in the old days. What you got was a blurred situation because of the limited resolution of spectroscopy, so you could not see any gap. All this changed because of two different factors. Number one, the advent of high temperature superconductors, since the superconductivity gap is related to the temperature, and so if you have a transition temperature that is larger, as in high temperature superconductors, the gap is a little bit bigger than that in a low temperature superconductor. This stimulated a lot of work, a big effort, in order to refine the photoemission techniques and start looking at energies that were very small, and therefore being able to get enough resolution to actually see the superconductivity gap. And finally, these efforts paid back. This is one of the very first, if not the very first case in which a high temperature superconducting gap was detected. This was the high temperature superconductor called BISCO. And you can see here the black spectrum from the normal state and the red spectrum from the superconducting state. And it is quite clear that at the edge, at the top end of the distribution, when superconductivity kicks in, then you are going to get a gap. In this case, again, we started from a purely theoretical kind of notion, and we went into something that you could go in the laboratory and see with your eyes. That's very satisfactory, but there is more to that. Okay, there is much more. Because, of course, once you can detect the gap in a direct way using a synchronous radiation photoemission technique, then you can become ambitious and start asking what are the properties of this gap. For example, is the gap in the general mechanism of superconductivity something isotropic that is equal in all directions? This is what is called in jargon the S-wave superconductivity, or is it not? Well, the experiments actually showed, excuse me, The experiments actually showed that the phenomenon is not isotropic, it changes with the direction, and this sets a very stringent condition for all the theories of superconductivity. And so that's another example. But now let me go back to microscopy. Can you take photon emission and transform it into microscopy? And the answer is yes. Okay. Instead of doing a photon emission analysis in a large area of the sample, you can concentrate on a small area. How so? Basically, we have two different strategies. The first one is to focus X-rays into a narrow area. And the other one is to process the photoelectrons with a device similar to an electron microscope. Both approaches are used very widely. And in both cases, what you're getting is no longer a spectroscopy. A spectroscopy is a technique that gives you information about energy and momentum, and therefore gives you information about the chemistry. But you can also implement that in a spatially resolved way and look at a microscopy. And if you put things together, you get what is called a spectromicroscopy. This is one example in which photon emission spectra were taken in different places in a sample in a microscopic way. And so you could actually see from the presence of core levels, the presence of the corresponding chemical elements, but the chemical elements are not present everywhere. More or less arsenic, gallium in this specific indium gallium arsenide sample are more or less in the same position, but indium is not. And so this gives you the real chemical maps about the specimen. That's the kind of microscopy or spectromicroscopy that is based on the photoelectric effect. Now, before, excuse me, no, I think that that's as much as I want to present today, because tomorrow we are going to have time to go into this last class of techniques, which is the microscopies that are based on scattering and diffraction, in particular crystallography. But I think that this is a good time to stop in time with the allotted slot for my presentations. And so I will stop here. Let me go back to spectromicroscopy. And before ending, I like to see once again if there are questions.
Sí, no sé si me oigan. Ah, muy buenos días. Buongiorno, Giorgio.
Oh.
Bueno, yo escribí una pregunta en el chat respecto a lo que mencionaste al inicio de la presentación.
Okay, then I will stop the sharing and go into chat, okay?
Sí, igual te doy el contexto en español. Tú mencionabas ayer que pues, la red de sincrotrones participó de manera significativa pues, para obtener la estructura del virus responsable de la última pandemia. Mi pregunta es, ¿cuáles sincrotrones específicamente fueron los que se involucraron o participaron en obtener la estructura? ¿O fueron entre todos un pedacito de la estructura? O no sé, si cada sincrotrón aportó de pronto según una línea de luz específica alguna información para obtener en conjunto la estructura del virus.
Prácticamente todos, porque las técnicas que se utilizan para estudiar las estructuras son típicamente técnicas de difracción, difusión de los rayos X, y son técnicas que son muy populares. Entonces, todos los sincrotrones tienen líneas de luz de este tamaño. Entonces, la gran mayoría, si no la totalidad de los sincrotrones han participado a la lucha contra el COVID. Pero quería presentar un fatto importante. La distribución geográfica ha tenido una consecuencia fundamental. Todos los sincrotrones que han participado a la lucha contra el COVID estaban en el hemisferio norte. El país de la América Central y de la América del Sur que ha participado, hay un solo ejemplo, que es Brasil, con con Sirius, que es el sincrotrón de Campinas. So that's, I think, is very important because if you want to start looking at, in a broad sense at what are the contributions, well, you need to start developing a fantastic network like the synchrotron network in the event that they are going to need them for specific analysis. Now, the COVID is one example. There are many other cases, but basically it is a weapon that you prepare to get ready for any kind of catastrophe. And pandemics can be predicted to occur because if you're looking at how many there were before COVID, well, there was the Spanish flu, there was the first Asian flu, there was a second Asian flu. I'm old enough to remember the last of these, and I can tell you it was very bad, and it took 6 years in order to control them, not the 2 years of COVID. So synchrotrons did make a difference, and to respond to your question, it was not an isolated example, but it was a widespread participation. The only difference was given by the problems in traveling and accessing, and each synchrotron had to find its own solution. I hope this answers your question.
Yes, and one last question: is there any publication, scientific publication that shows these results?
Oh yes, there is a truckload of publications because people were not making any money, and so they published as much as possible. Actually, I would suggest you to start looking at the review articles. There are pretty good ones, for example, in the CERN website that gives an oral description, and then you can look, starting from that, at the contribution of different facilities. In particular, look at the Sirius website, and they explain how they solved one of the crucial problems the start of all this fight.
Okay, thank you very much.
You're welcome. All right, other questions? Ya, yo soy aquí. All right. Now, let me tell you that this is the technique that we are going to present at the beginning of the lecture tomorrow. It is the technique that for which I just showed the first transparency, but without going into the first transparency. Basically, you are using scattering slash diffraction, which is the mechanism that is complementary to the mechanism of absorption. So if you're taking the complex refractive index, in the complex refractive index, there is an imaginary part that gives you the absorption, and there is a real part that gives you interference, scattering, and so on. So almost all the experiments that are studying structural techniques using synchronous radiation for viruses are based on this class of techniques, and we elaborate tomorrow how they work. Let me just make a long story short by mentioning that the basic fact is that if you're looking at the X-rays that are emerging from the interaction with the specimen, and you're looking at their intensity distribution, you can theoretically demonstrate that this is basically the Fourier transform of the charge distribution. So you can think of a very simple way, that is, if you are now measuring the intensity after the interaction, you can apply an inverse Fourier transform and go from the scattered intensity to the charge distribution of the electrons. So this is the basic idea of all these class of techniques. Now we need to elaborate a little more tomorrow about the details, but that is the basic ideas, and also this is what causes all the practical problems. So let's be patient until tomorrow. See? È una questione, sì, è una questione di intensità. Well, I think it's probably better if I answer to you in English or in Spanish, but let's say English, because I can tell you in Italian, but it's going to be between the two of us. It's a question of intensity. Okay, suppose, for example, that for the emission spectrum, you're getting a core level that is related to a certain metal, like gold, all right? Now, if there is a small amount of gold, the intensity of the peak is going to be small. If there's a bigger amount of gold, then there is a more intensity in the bigger peak. So this gives you the amount of gold that is present. The real problem is that if you do not have a spatial resolution, that is, you're not implementing things in a microscopic way, you just get the average, okay, over the entire sample. This may be good in some cases, but it's not sufficient in many other cases. And that's why there was the struggle in order to improve the sources and so on. So now we have enough intensity of X-rays so we can go with lateral resolution and distinguish what is the composition in different portions of the sample, okay? So microscopy is the other component. Okay. No problem, I'm here. Still early for me. Thank you, thank you, thank you, because this was one of my very first personal results. Okay, that is what we did, for example, was to take for the emission spectra using different kind of polarization for the photons, and so we could distinguish between initial electronic states of different parity. Okay, and so this allowed us to make some fine analysis of the electronic structure, not only the generic electronic structure, but also the parity of the electronic states. So that was a rather popular technique for a few years when I was a kid. Okay, you're talking about the late 70s and early 80s. In these days, things were adventurous because in order to change the polarization, you cannot rotate the ring. So the only choice is to rotate the sample, which sounds very easy, only that the problem was that the sample is in a vacuum chamber, okay? And so you had to rotate the entire damn vacuum chamber while keeping the connection to the main storage ring and hoping for the best, that is that they're not screwing up the vacuum for the entire group of users. So it was an adventure. No, insomma, of course, there was a lot of work going on, but there were other synchrotrons that made important contributions. In some cases, Leo, it's even difficult to make an assessment, okay? Because suppose that a synchrotron comes with a structural detail 1 week after another synchrotron. Is this an important thing? Yes, because it gives confirmation. Okay, you don't want to start a huge enterprise to product a virus by looking at a number of compositions that match the structure without having some corroboration of the initial results. So it was really an example of collective work in which the individual publications after all, were not that important. Okay, it is difficult to identify somebody who came out by saying, "This is the touch of the virus," and I beat all the competition. It was a collective effort, and it is also reflected in the citations and so on. All right. Perhaps, yeah, perhaps, Leo, in this way, we got to a new level of maturity about doing science. Absolutely, yes. Okay. And that, yeah, Yep. Absolutely, Leo. And no, I'm astonished that I didn't know this is not a secret. It is a public fact. You just go into the CERN literature and you find a narration of these events. And as I mentioned, it is also like a mystery movie in which you find that you have to beat the virus over time. And the Chinese were making this phone call in order to stimulate the English colleagues, the British colleagues to take over. That's the truth. Okay, it's not a secret. It's available for everyone. But as you probably, unfortunately, know, uh, bullshit is much more sexy than serious information. All right, and so the simple fact that shows that actually the Chinese colleagues were behaving in a very responsible way, forgetting about priorities or secrets and so on, and they just went and made the information available to everyone. All right, that's the fact. The rest is BS. Yes, no problem. I think that I'm also delivering. No, but you know that really the case for a synchrotron in Africa, a synchrotron in Caribbean, and so on is compelling. And if you can start presenting the facts, okay, for example, the 1 to 1,000 ratio between savings from research and investment for research, well, maybe people will start thinking about that. I have a number of sexy facts that I not that did not present today because they are also politically dangerous. For example, the entire network of synchrotrons, the cost is 10% of the system of big cruise ships for this, this huge zoo-like cruise ships that are causing a lot of problems around the world. 10%. Oh, Yes. Okay. So until tomorrow then. All right. Thanks.